In this video, I am going to continue evaluating some derivatives. You'll notice from the screen that this is part 3, and there's so far I believe this is going to end up being 3 videos total. And what happened is I was in the middle of evaluating some derivatives in the last video, and the tablet froze up. So rather than figure out how to fix that midstream, I simply ended the video and we'll resume here, and we'll just call it a third video. But if you do find this video helpful, you may want to search for that part 2 video, which evaluated a few more derivatives. And then part 1 video did some other problems, such as using the difference quotient definition of a derivative to evaluate a derivative, and an example finding the equation of a line tangent to a function, which used derivatives. But in this example, we're going to apply the power, or not the power, well, we will apply the power rule, but mostly we're going to be looking at the product rule for derivatives. So I've written that rule out here, and I would model that. It's a good practice to write that formula each time you're going to use it. So the derivative of a product is the derivative of the second factor times the first factor, plus the first factor times the derivative of the second factor. Off to the right here, you can see that I've worked out each of the derivatives. So I would suggest writing this step out also. F, the x to the 7th plus 6, is the first function, or the first factor. And g, x to the 5th plus x to the 4th plus 3x plus 2. Oh, I see that I left off that plus 2 here. Is the second factor. Let me write in that plus 2 before we go too far. And then when I do the derivative of each of those functions, I see that the derivative of f, the derivative of x to the 7th plus 6, is 7 times x to the 7 minus 1, or 6. And the derivative of the second factor, g prime, is 5x to the 4th plus 4x cubed plus 3. And then the derivative of 2 is just 0. When I fill these in to the formula, to the product rule, f prime is the 7x. The derivative f prime is the derivative of the first factor, so the derivative of x to the 7 plus 6 is 7x to the 6th power, times the second factor, that's x to the 5th plus x to the 4th, I'm going to copy it carefully, plus 3x plus 2, plus the first factor, that's our x to the 7 plus 6, times the derivative of the second, 5x to the 4th plus 4x cubed plus 3. And now what's next is I'm going to distribute each of these, and this is where it does get a little bit messy, and that's okay that it's a little messy. Don't let that panic you. Just do it carefully, and it'll be fine. I'm going to distribute the 7x to the 6th to these 4 terms. What does that look like? 7x to the 6 plus 5 is 11. 7x to the 6 plus 4 is 10. 7 times 3 is 21. X to the 6 plus 1 is 7. 7 times 2 is 14. X to the 6. Next, I'll distribute this x to the 7th to each term. So plus 5x to the 7 plus 4. So 5x to the 11th. And, you know, before I start writing these, let me show you a good approach so that when I get to the next step, which is combining like terms, it just flows a little bit easier. Since this is x to the 11th, why don't I write it right under the x to the 11th term? So x to the 7th times 5x to the 4th is 5x to the 7 plus 4, or 5x to the 11th. And then x to the 7th times 4x cubed. 7 plus 3 is 10, so it's going to fall right under this term. So 4x to the 7 plus 3, 4x to the 10. And then x to the 7th times 3 plus 3x to the 7th. Now last piece here, we will distribute the 6. 6 times 5x to the 4th will give us 30x to the 4th. 6 times 4 is 24x cubed. 6 times 3 is 18. When I add these together, when I combine the like terms, I get the final answer of 7 plus 5. 7 plus 5 is 12. X to the 11. 7 plus 4 is 11. X to the 10. 21 plus 3 is 24. X to the 7. And then everything else has no like terms. We have an x to the 4th, an x to the 4th term, an x cubed term, and then a constant. Notice that as I've written these, I've put them in descending order. That's just best practice to put them counting down the exponents: 11, 10, 7, 6, 4, 3, and then the constant at the very end. That's the product rule. You see, it's not that challenging. It's a little messy, and with some careful work, you can get that right every time. Let's look at the derivative of a radical. Now, remember, we've got to think of this as this radicand being in parentheses. This x cubed minus 2x is like a piece in parentheses. So we're going to see this as the composition of two functions. We're composing the 6x cubed minus 2x with a square root. So we're going to have to chain. To start with, I'm going to recognize that the derivative of a square root is 1 over 2 times the square root. I've just memorized that formula, that pattern. You could work it out as the power rule for x to the 1/2. Then I've got to remember to chain. So I'm going to say times the derivative with respect to x of the 6x cubed minus 2x. So the derivative of 6x cubed minus 2x is 18x squared minus 2. And then I have that over 2 times the square root, 6x cubed minus 2x. You might notice that you can factor a 2 out of everything. So we could see this as 2 times 9x squared minus 1 over 2 times the square root. So when I divide out the 2's, I'm left with 9x squared minus 1 over the square root of 6x cubed minus 2x. That's important to notice this chaining. Let me highlight that. It's important to notice that we have to chain the derivative of the radicand. So we did the derivative of a radical, the square root, times the derivative of the radicand, the 6x cubed minus 2x. This next example is applying the product rule. So I'm going to write out the product rule formula. The derivative of a product is the derivative of the second factor times the first factor, so f prime g, plus the first factor times the derivative of the second factor, so f g prime. Off to the right, I've written now the second factor is x to the 4th plus 9, and its derivative is 4x cubed. The first factor, sine cubed of x, I could see that, by the way, the notation means sine x cubed. So sine x times sine x times sine x. When I do the derivative of sine cubed x, I've got to remember to chain. So it's this exponent 3 times sine x to the 3 minus 1 or 2. But then I've got to go back and get the derivative of sine, which is cosine. When I write this 3 times sine x squared, better way to format that is to write 3 sine squared of x. And then times the derivative of sine is times cosine of x. So the derivative of sine cubed of x is 3 sine cubed of x times the cosine of x. Just filling each of these in. Once I've written these notes that I have off to the right, once I've done this legwork, filling them in is a pretty easy process. I've already got the derivative of f. Let me use the same color so that if you're distracted at all, you might be able to follow the colors here. 3 sine squared of x, cosine of x, times the second factor, so that's the x to the 4th plus 9, plus the first factor, sine cubed of x, times the derivative of x to the 4th, which is 4x cubed. Now if I distribute, I can add, so x to the 4th times, let me show you what I'm distributing this. 3 sine squared x cosine x distributed to both x to the 4th and 9 would be three x to the 4th sine squared x cosine x. So that's 3, and then here's the x to the 4th. Plus, now I'm going to distribute the 9. 9 times 3 is going to give me 27 sine squared x cosine x. Plus, I could distribute this 4x cubed sine cubed of x. So I could write it like this. I don't see anything that has to be factored consistently, like a common factor to pull out. Well, actually, I take that back. We could factor out a sine squared, it looks like. But, you know, really there's no need to. Depending on what your purpose is, you don't have to do this. If the fine print gives you these directions that say, write your answer in fully factored format, then we would want to factor out the sine squared. But I would say it's okay to leave it as it is. Let's look at this next example, tangent squared of 5x. This is an excellent example of applying the chain rule, because you have to chain not once but twice. Let me show you why. To start with, I'm going to see this tangent of 5x. So let me rewrite this. Tangent squared 5x. That is the same as saying tangent of 5x squared. So when I go to do the derivative, I'm going to get 2 times the tangent of 5x to the first power. Then I've got to go back and do times the derivative with respect to x of tangent of 5x. When I chain that first layer, we'd have 2 tangent of 5x. The derivative of tangent is secant squared. So the derivative of tangent of 5x is secant squared 5x But wait, there's more. I have to say times the derivative with respect to x of 5x. Now that derivative is 5, right? So let's write this last layer. Y prime equals 2 tangent of 5x times secant squared of 5x times 5. The derivative of 5x is 5. The last step is probably going to be to move this 5 up to the front and multiply it by the 2. So I could say that the final answer might look like this. Y prime equals 2 times 5, or 10, secant squared of 5x times the tangent of 5x. I could simplify that. I could do a little work with the secant and the secant squared and tangent, but there's really no reason to have to. I think it's fine to leave it like this. Let me show you what I'm referring to. If I looked at secant, it's 1 over cosine. So let's see what happens. If I did secant squared, it's 1 over cosine times cosine. And tangent is sine over cosine. So you might see it as sine over cosine cubed. But really, I think it's fine to leave it secant squared of 5x times tangent of 5x also. Let's go on to another example. Oh, actually, that's the last derivative we have. The last part is going to be evaluating limits, but I'm going to save that for another video. If you are interested in seeing some limits, then look for the next video.